Okay, good afternoon, good morning, good evening, everyone. Welcome to our seminar. And today is my great pleasure to introduce Professor Francisco Periago. Francisco Periago is full professor in applied mathematics at the Universidad Politécnica de Cartagena in Spain. And today, Professor Francisco Periago is going to talk about an introduction to machine learning-based method for control of PDEs. Thank you very much, Francisco, for accepting our invitation, and the word is yours.
Okay, thank you very much for your kind invitation. For me, it's a real pleasure to be here. I remember I was in Rio in 2003, invited by Professor Gustavo Perla Mensala. So for me, it's a pleasure to be with the Brazilian community in particular. Well, I'm going to talk about control and machine learning. So let's start with control. So just for the sake of simplicity, let's consider this linear control system. So here, A is a linear operator, Y is the state variable, U is the control. The control is acting through the system by an admissible operator B. So it means that you may act in the interior of the domain, on the boundary, etc. Okay, so given a positive time, capital T, and a target state yt, the exact controllability problem for this system amounts to finding a control U such that the solution, the associated state Y, satisfies this controllability condition. Okay. Well, the main goals of this presentation is to try to solve this type of problems by using machine learning methods. So precisely, I'm going to talk about two different problems. So in the first one, we are going to fix the initial condition y0, and then we are going to compute the control U, not by using polynomials or piecewise polynomials, but by using neural networks. And in the second problem, we will try to learn the whole controllability map. That is, we are going to compute just only one neural network for all initial conditions y0. And the key point here is that, as all of you know, there are many methods, starting from the pioneering works by Lyons and Glowinski. I mean, there are many methods to solve this type of controllability problems. So the key point here is to try to not to compete with those methods based on finite elements or finite difference. The key point is to try to propose methods that break the course of dimensionality phenomenon, according to which the time complexity of the algorithm grows exponentially with the spatial dimension. So it means that we can solve this type of problems in dimension 1, 2, 3, but in higher dimension, the cost is really unaffordable. And there are many control systems in high dimensions. So for instance, control problems coming from quantum mechanics, the Boltzmann kinetic equations, among many others. So that's the point where machine learning-based methods can make a difference, right? Okay, so let's start with the first problem. So let's consider this toy model. This is just the boundary Dirichlet new control for the wave equation. So here we have the linear wave equation, the initial conditions. On a part of the boundary, there is a zero Dirichlet boundary condition, and the control is acting on the rest of the boundary. And again, our goal is to compute a control U as the solution associated to this control satisfies this null controllability condition. The method that I'm going to propose is based on famous physics-informed neural networks. This is a method that has been introduced in this seminal paper a few years ago, and it has been very successful in solving forward and inverse problems for both linear and nonlinear partial differential equations. So what I'm going to present is just an adaptation, extension of this method, this methodology. Okay, The algorithm is composed of several steps. So in the first one, we are going to fix the approximation space, or the hypothesis space in the terminology of machine learning. So we are going to consider not polynomials, but neural network. So in particular, I'm going to consider this architecture of neural network. This is a multi-layer perceptron. So we are going to approximate the state variable of the control system by this y hat. And this y hat is defined as follows. So first, there is an input channel or an input layer in which or through which we introduce the spatial data, x, and time data, t. So imagine that here we have two numbers. Then we are going to produce three different numbers in this first hidden layer. So how can we compute this number? Well, this is very easy. What we do is just to multiply these two numbers, xt, by a matrix of suitable dimension. Then we add a bias, a vector, right? And then component-wise, we compose by an activation function, sigma. So for instance, the hyperbolic tangent, which is smooth, right? So now here we have three numbers, and then we compute another 3 or 4 numbers. In the same way, we just multiply by another matrix, and then we add a bias. And again, component-wise, we apply the same activation function or another one. And finally, the output, y hat, is just computed by multiplying the last 3 numbers by 3 another different numbers, right? So here, the parameters of the neural network are the entries of the matrices and the biases. And this is what we call ball theta, right? So these are the unknowns. These are like the coefficients of the polynomials when we are doing a polynomial approximation of a function. Okay, in the second step, we should consider some training data set. So for instance, imagine that the physical domain is the interval 0, 1, and the time domain is the interval 0, 2. So what we do is to select some points in the interior of the domain, typically random or pseudo-random points. So this picture corresponds to solver points, and also some random points along the boundary of the domain. So the xt are called in the terminology of machine learning the features. Then we need labels to associate to each feature a label. Labels will be equal to 0 in this setting. And finally, we need a loss function. The loss function is just the residual of the PDE, the boundary condition, the initial conditions, and the final conditions, right? The terminal condition, the controllability condition. In this case, both are equal to 0. And this W that appears in this formula are just suitable weights for some quadrature rule, right? So putting all things together, we obtain the loss function, capital L, right? And the unknown of this function is the vector theta of the parameters of the neural network, right? So, and here we have the y hat, which are the neural network that I have presented in step 1. So finally, we solve numerically this nonlinear, highly dimensional nonlinear programming problem. So we get some optimal theta star, right? So then we can use this theta star to put the theta star here, right? And then we can make predictions. We have an approximation of the state variable. And if we compute the trace of the state variable on the boundary gamma c, then we get the control u hat, an approximation of the control. So to sum up, What we do is to insert the neural network, an approximation of the state variable, into the PDE, the initial conditions, the boundary conditions, and the controllability conditions. So then we define the loss function, capital L. We minimize with respect to theta, the parameters of the neural networks. We get the theta star. Then we have what we call the pin state, an approximation of the state variable of the control system. And by computing the trace on the boundary gamma C, then we get the pin control, right? What about error estimates for this scheme? Well, there are two main concepts in different concepts of error in machine learning. The first one is the concept of training error. Training error is just the value of the cost function after convergence of the algorithm. That is, once we have compute theta star, then we put theta star in the cost function, and we get, what we call the training error. Ideally, this error would be equal to 0, but in general, it is not. Okay. So this is training error. Yes, the value of the cost functions at the theta star, the optimal theta star. And then there is the concept of generalization error for both the control and the state variable. So this is just the L2 norm of the difference between the exact control of the problem U and the pin control, the approximation of the control. And the same for the state variable in the space where the solution lives. So then it can be proved that if the state variable and the pin state variable are smooth, class C2, then this generalization error can be bounded by constant times the training error for the interior of the domain, for the PD, for the boundary condition, initial conditions for position and velocity, and the same for the final or controllability condition for position and velocity. Plus these quantities, and these quantities are just or comes from a quadrature rule. The error estimates for a quadrature rule. So here, capital N are the number of interior points that I have showed you before, or the points on the boundary, etc. And this alpha depends on the smoothness of the function that we are going to approximate, right? So these are just quadrature errors. So it is important to emphasize that this constant depends on the domain and the final time. So as a consequence, C may depend on D, on the dimension, the spatial dimension of the problem. Okay, the same holds for the state variable. And also it can be proved that if the size of the neural network, the number of parameters in the neural networks, and the number of training points go to infinity, then training error go to 0. So the conclusion is that these two contributions go to 0, and as a consequence, also the generalization error. So people usually say that if the algorithm trains well, meaning that training error goes to 0, then it also generalizes well, right? Okay, so let me explain you briefly the idea of the proof, which is quite simple. So the idea is just to consider the difference between the exact state and the pin state, the same for the control. Then by linearity, it is very easy to see that Y bar is the solution of this problem. This is a non-homogeneous wave equations with initial conditions, with final conditions, and boundary conditions. Then we can decompose Y bar as Y1 bar, Y bar 2, and Y bar 1 accounts for the initial conditions and this part of this boundary condition. So the non-homogeneous term in the wave equation is accounted for Y bar 2, and the same for the final conditions and this boundary condition. Then we are going to do is to apply an energy estimate for system 4 and an energy estimate for system 5, right? So then this first inequality is just a typical observability inequality in controllability theory. This is, let's say, the cause of the control. So it is bounded by some constant Z0 times the initial conditions and the final conditions, right? Then this second inequality, what we do is just to use that y bar 1 is equal to y bar minus y bar 2. And we use the conditions, I mean, we use the PD that is satisfied by both functions. So then these two terms are replaced by these two other terms. And here we have also used that L2 is continuously embedded in H minus 1. And finally, what we do is just to apply an energy estimate to this term. So we obtain another constant, the energy, the constant due to this energy estimate. So we have here the boundary condition and the non-homogeneous part in the wave equation. Remember that y hat, the initial conditions here are equal to 0 for y bar 2, and that's why they do not appear here in this expression. And then once we have these different terms, what we do is just to apply a quadrature rule, and then what appears are the terms corresponding to training error and the bounds for the quadrature rule. And the fact that the training error converges to 0 is a consequence of the celebrated Pincus universal approximation theorem that I'm going to revise in a few minutes. And it basically states that any function of class CK may be uniformly approximated in the norm CK by a suitable two-layer neural network. Okay, this is a numerical experiment for the 1D wave equation. These are the initial conditions, and this is what we get. Actually, the error is of the order of 2%, and we have used a neural network composed of 4 hidden layers with 50 neurons, 50 units in each layer. The Python codes are available in this GitHub folder, and here you may get the scripts for the linear wave equation, which is the experiment that I have shown you right now, but also there are some experiment in high dimensions for instance, for the heat equation. Okay, to conclude this first part, some comments and related open problems. So the first one is that, although for simplicity, I have presented just results for linear problems, the PIN algorithm generalized to any control system, both linear and nonlinear. The algorithm is essentially the same. Another thing, another history are the proofs of the generalization error, the estimate of the generalization errors. So a very interesting problem, maybe an easy problem if you are an expert in observability inequalities, is to try to guess or to try to know the dependence of these constants with respect to the dimension D, and try to know if the dependence is exponential or not, because the conclusion is that we can break or at least alleviate the phenomenon of the course of dimensionality, right? And then we can extend, let's say, the algorithm to higher dimensions. Another interesting issue is that the proof uses linearity. I am a half-glass full person and optimistic, and I do believe that similar estimate on generalization error can be obtained at least for semilinear PDEs, right? But I have no time to think on it. And similar problems can be addressed for inner or Niemann controls, etc. Okay, so let's now move to the second problem. So far, we need to train a neural network for X fixed initial datum. So problem 2 amounts to find just only one neural network for all initial conditions. So problem 2 then amounts to learn from a data set the controllability map. Okay, what is the data set? Well, the data set is composed of a number of initial conditions, y0j, evaluated on a set of sensor points. So for instance, imagine the interval 0, 1, so a number of points in the interval 0, 1. And these are referred to as features in the terminology of machine learning. And their corresponding controls, uj, evaluated at some discrete times t, right? And these are the so-called labels. So the matrix of data is this one. I mean, initial conditions and controls. Okay. An important remark of this problem is that the controllability map is in general is not a single valued. It is set valued, right? So it means that the controllability problem may have many solutions, actually, an infinite number of solutions, right? So this question naturally arises. Is there a selection, a single value map, such that interpolates the data set? And in such a case, how smooth is this selection? But the answer is yes. There are Lipsy continuous selections. So for instance, controls of minimal L2 norm are Lipsy and continuous. But there are some details that should be addressed. You may find the detail in this preprint, right? Okay, so sorry. Let me now explain the machine learning setup for the problem. So let me recall again how to compute the data set. So first, we fix a set of sensor points, for instance, in the interval 0, 1, just to fix ideas. So then the information of each selected continuous initial datum y0 is encoded in a vector, in this vector. Then we also take a time in the interval 0, capital T, and the corresponding labels are the control associated to this initial condition, right? Second step is to consider, again, an approximation space. In machine learning, people say a hypothesis space. I mean, the type of neural network. So for this specific problem, we're going to consider the so-called deep ONEP, which takes this form. I'm going to explain right now where this expression comes from. But for the moment, let's keep in mind that the parameters of the neural network are the C's, the Psi's, the theta that appear here, and that the W here, and the eta that appears in this neural network. And finally, we need a loss functions. The loss function for this problem would be just the mean square error between the predictions made by the neural network, the deep ONET, and the exact control, the labels of the problem, right? Okay, why deep ONET? Well, deep ONET is composed of two main networks. The first one is the so-called branch net. This is actually a multi-layer perceptron, the same structure as the one that I have considered in problem 1 before. And the second one is also very simple. This is the so-called trend net. It's just to multiply the time by a parameter and to add a bias, and then the composition with an activation function, which could be the same or a different one, right? And then basically we multiply both. So here we have the branch net, and here we have the trend net. And we may add this term in order to make, I mean, the neural network affine with respect to the trend net. And schematically, the process is as follows. We are going to approximate an operator with two function spaces. So the first thing is to use an encoder, just to replace a function by a vector. Then we perform a finite dimensional approximation of the operator. So we go from Rm to Rp. And in this process, we use the branch net. And then we should go from a vector to a function. We need a reconstruction operator. And in this process, we use the train net, right? As you will see, this type of neural networks are going to produce very nice results. We find the reasons in the universal approximation theorems in machine learning. There are many different types of universal approximation theorems for functions, for functionals, and also for operators. The first one is the celebrated Pincus universal approximation theorem, which says that any continuous functions may be uniformly approximated on compact sets by a two-layer neural network, in particular for a multi-layer neural network. Here, sigma should not be a polynomial, so typically should be the famous ReLU activation function, which is just the maximum between S and 0. And moreover, it is proof that these constants actually are continuous linear functional defined on U. Okay, then there is an extension of this universal approximation theorem to functionals. So now F is not a function, but a functional, right? And then it can be proved that also by using under compactness hypothesis, any continuous functional may be approximated by a neural network, which basically has a similar structure as the previous one, right? So here we find the encoder, right? When we replace the function u by the vector uxj, right? And okay, and finally, if we combine these two theorems and we work again on the compactness hypothesis, then what we can prove is that any operator can be approximated by, let's say, a finite number of functionals. So if we replace this ci by this expression, remember that this is a continuous functional, then what we get is the structure of the deep O-net. Okay? Again, the key point is to try to break the cause of dimensionality. In this setting, the cause of dimensionality reads as follows. We say that imagine that we take a deep O-net providing an error less than epsilon. Universal approximation theorem says that this type of neural network exists, right? So the size of the neural network is the number of non-balancing parameters of the net. I mean, the entries of the matrices, the biases, all these parameters. In general, we need a neural network of size of the order of epsilon 2 minus theta epsilon. If this theta epsilon goes to infinity when epsilon goes to 0, then we say that the deep O-net algorithm incur a cause of dimensionality. But if the limit is finite, then the cause of dimensionality is broken, right? So in principle, there are very bad news because Jaroski proved in 2018 that the approximation of a general Lipschitz function to accuracy epsilon requires an ReLU network of this size, where M of epsilon. M of epsilon is the number of sensor in the encoding operator, right? So when epsilon goes to 0, then this exponent goes to plus infinity. And as a consequence, we are suffering from the cause of dimensionality. But our problem is simple. I mean, the function that the operator that we want to approximate is richer than only Lipschitz continuous because it's linear. In fact, our operator, the contrariety map is linear, right? So that's why we are able to break the cause of dimensionality for this specific problem. So for now, in this part of the talk, I'm going to use this seminal work. And I'm going to talk first of approximation error. Well, approximation error is just the distance between the operator that we want to approximate and the space, the hypothesis space. So this is approximation error. So here there is integration with respect to t. So here g, y is the control depending on t, right? And this is the deep omnet that is going to approximate the controllability map. And there is also an integration in L2. This is a Wagner type integral. So here mu is a probability measure, right? Okay, so this error can be decomposed into three main components. First is the encoder that I have mentioned before. Then there is the, let's say, the approximation operator in which we approximate the finite dimensional operator by an operator. And the key point is that for this specific problem, this operator is linear, right? We are going to use the branch nets to do this job. And then there is the reconstruction operator, right? In which from a vector, we get a function. This is, let's say, similar to a Fourier approximation of a given function. And then the trans nets are going to make the job for this part. But our setup is that we are going to consider a second order probability measure, right? Typically, we consider the covariance operator, and we get the eigenpairs, the eigenfunctions, and eigenvalues. The sensor points could be, for instance, uniformly distributed in the interval of the domain we have considering. The decoder is the inverse of the encoder. We may consider a linear decoder. And for the reconstruction operator, we take the first p eigenfunctions of the covariance operator. Here, this is the push forward measure through the contrariety map capital G. And the inverse is the projector operator, right, on this finite dimensional space. Okay, so in practice, mu is chosen as the law of a Gaussian field. For instance, a smooth Gaussian field. So these coefficients decrease exponentially. And in this setting, if we take the number of sensor points of this order and p, which is the number of terms for the reconstruction operator, the number of eigenfunctions for reconstruction, then it can be proved that approximation error less than or equal to epsilon may be achieved with a small deep omnet, actually a branch and trunk nets which satisfy these estimates. And in practice, what it means is that for this specific problem, the cause of dimensionality is broken, which is a very good news. Okay, there is also the concept of generalization error. Well, the concept of generalization error is that in practice, we do not solve, we do not minimize this functional. What we minimize is an approximation of this functional. Specifically, what we do is to apply Monte Carlo integration for integration in L2. So then we get some functions here, right? And then we apply another quadrature rule for integration in U. Just for simplicity, here I have considered a midpoint rule, right? Okay, so let denote by n hat the optimizer, let's say the optimal optimizer, the optimizer of this functional, and by n hat n, which depends on the number of functions that we take in our data set, the optimizer of 8. What is generalization here? What generalization is just the difference between this optimal value and the value that we get if we put the optimizer of this functional in this original functional from the beginning, right? Well, here this is a bit technical, but anyway, it can be proved that generalization error is up to a log of the order of Monte Carlo, which is the best that we may get in this setting. Here, there are some hypotheses that are trivially satisfied by our neural network. This is not a problem. The only inequality, the only assumption that should be analyzed with attention is this one. But this one is like a uniform observability inequality, because this is more or less like that the control is bounded by the initial conditions, right, of the problem. Okay, and now let me show you, just to conclude, a numerical experiment. So we have considered this kernel, which is smooth. This is exponential quadratic kernel. L is the correlation length. So we compute the eigenvalues of eigenfunctions associated to this kernel, right? And then we consider its Karhunen-Loew expansion. So this is the way in which we generate initial conditions data. We just consider a finite number of eigenfunctions and eigenvalues from the highest to the lowest, and we sample this random variable, then we get all the initial conditions that we want, right? Okay, so that's the way in which we have generate the data for the initial conditions. For the controls, we can use any classical method to compute control, or even the pin method that I have presented in the first part of the talk. Okay, so we have used an ReLU activation function and a very small deep on it with trunk and branch depth and width of the order of 240, which is actually very small. For training process, we have used ADAM, which is the most famous for the moment, is the optimizer of choice in machine learning, at least for this type of problems. Initialization of the parameters has been carried out by using Cloud Uniform. And the implementation, we have used this software, okay? And this is what we get for this academic example. Again, the wave equation, for which we have an analytical solution of the control based on D'Alembert formula, okay? And this is the evolution of the, this is the log history of the algorithm, right? This is quite typical. Number blue is for train, orange for test. So as you can see, basically the generalization error, the test error, is going to converge to 0, which is a very good news, right? And these are some outputs that we get for smooth initial conditions and also for non-smooth initial conditions. This corresponds to y0, y1 equals to sinus, and this one corresponds to this discontinuous initial condition for y0, velocity equal to 0. And we get errors of the order of 1% in this case, and less than 4% in this other case. Okay, that's all. That's all that I have prepared for you today. Thank you very much for your attention.
Thank you very much for your very nice talk, Francisco. So we open now the turn for question comments. So if anyone has a question or comment, please just do it.
Paco, I have a question.
Yep.
I'm Carlos Castro.
Yeah.
So in your first model with the pin, so this neural network intends to simulate the PDE, no? This is basically what. So you have fixed the initial data, and then the neural network tries to simulate these dynamics, no?
Exactly. Yeah.
That's the point. So what I wonder if you can combine this neural network, maybe it's your second part of the talk, but you can combine this with some more classical neural network that somehow combines the values of the initial data with the control. So, I mean, is there a way, maybe, or you have thought in a way to make the values of the initial data, so to be also parameters to be in the neural network? Do you understand what I'm saying?
No,
Maybe I'm not.
No, not really, Carlos. I don't know what you're saying.
Here, the initial data are constants, no?
Fixed, yeah.
Fixed constants.
From the beginning,
I wonder. So, but these machine learning techniques usually do regressions. So they combine numbers with numbers.
Yeah, no? Exactly.
So now you have a tool that for a constant value gives you the control.
Yeah.
So that relates that. No, now can you somehow now consider instead of one single initial data, you can make a neural network to learn how this relation between this initial data and this control are related? Maybe
well, this
do you
is
understand
actually
my question? Or?
Yeah, well, if I understand well, this is the second part of the talk.
This is basically the second part. But it is more in your second part. You look at this as an operator, no? It is it's basically the second part.
Yeah.
So this is what you are trying to do in the second part is to make this in a more functional framework, no, in a better functional framework. No, is that correct? No.
And this is actually the only point in which this technique may outperform the classical methods base that you have developed and many other people. I mean, because once you have computed the deep on it that approximate this operator, right? Then the predictions are very, 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 very quick, you know?
Yeah.
Maybe they are not, I mean, less accurate that if you perform finite element method, something like that, but we get the control quickly.
And a second question is, in this second method, how, imagine that you have trained the network with some initial data and some, so no, if you, for instance, train the network with some initial data and you take something a little bit different, it is very, so imagine that you train with data which is between -1 and 1, the initial data, and then you put a control for something which is takes the value 2. You understand what my point?
Yeah. Well,
this breaks a lot, or
no.
Well, this is inside somehow.
Well, actually, in that case, the process would be to how do you say, to standardize the data.
Yeah.
Okay. So you should transform your data to 0, 1 or to -1, 1, right?
Yeah.
This is like an scalarization of the data, right? This is what typically should be done. Yeah.
Thank you, Paco.
Okay, you're welcome.
Diego, I have another question.
Yes, please.
Yeah, Francisco, thank you very much for your talk. Again, for the first part, for the first problem, when you put the loss function, the loss function, yeah, here, the second part, the associated to the boundary, no?
Yeah.
L gamma D. This is for the part of there is an homogeneous boundary condition, or also
Exactly.
for
Exactly.
Okay.
This is for this part here.
Okay. Okay. And so for the you don't put a loss function in order to minimize the norm of the control, no?
No, no.
Okay, because in principle you could do that, no? Because
Yeah.
there is a control of minimal and to norm. In fact, is the one that you choose that you use in the second part, no?
Yes, we can put this. Yes.
Okay, but you didn't put it in this. I don't know, maybe in some simulations or I don't know.
But I think that this is not difficult to include here, right? We could add another term to minimize the control. Yes.
Yeah, because maybe even if you didn't put it, the algorithm is finding the control of minimal L2 norm.
Yes. Yes.
Yeah.
I guess. Yes. Yes. Yeah.
Okay. But by chance, well, it's good luck, no? Or
No. Well, you should. I mean, you should combine some weights because I mean, you aim to minimize all these contributions.
yeah.
In particular, I mean, you should minimize the controllability condition. So this should be equal to 0. So if you add here another term for the control, then you have to weight it properly.
Okay.
You know.
Okay. Yeah, well, I think that
Yes.
it's hard to maybe to say something, but
Well, there is in this type of methodology, there is always a tuning process. You should, I mean, tuning the parameters, the weights that appear in the loss function.
okay.
I have not tried what you say, but I'm confident that this would work. Yeah.
Thank you.
Okay.
In the chat, we have also some questions. Is by Ed Tari Fawad. He said that, or she said that, thank you for this interesting talk. I have two questions. What about the case of internal control? Is there a method to choose the weight of the loss function?
Well, the first question can be addressed. Yes, I have written it as an open question here. Inner control, Neumann control, yes, it can be addressed. In the problem that I presented, the situation is simple because the control is at the trace of the state variable. So we just need only neural network to compute the state variable, and then let's say the control is like a gift, right? But of course, this problem could be addressed. But in that case, we should introduce two neural networks, one for the state variable and another one for the control variable. And the second question, can you repeat, please, Diego?
Is there a method to choose the weights of the loss function?
No, there is no way. Yes, you should try an error. I do think that there is not let's say an optimal value of the parameters of the weights in here, these weights, right? Yeah. No. Well, this comes from quadrature rules. So, well, there is, I mean, depending on the quadrature rule that you are going to use, there are the corresponding weights. And this is, I'd say that this is the optimal choice of the weights. I mean, the weight that we should consider in the loss function.
Good. I have also some. So he said, thank you for this interesting talk. Okay. The first one is that at the beginning, you say that this technique could be interesting to address some high-dimensional problems, right?
Yeah.
And you present a numerical simulation in 1D.
Yeah.
So you have experiments in.
Yes, in higher dimensions. Yes. Well, this is a first step. So we should go step by step, right? So the first thing is to take example where you have analytical solution to try to see the methodology works nicely in these simple problems. And then you try to go to higher dimensions. Yes, in this paper, we have addressed another problem with a heat equation. Here there is the code. In dimension, I remember it was around 10 or something like that. But yes, 10, 100, 1000. I mean, there is no problem to extend. But in order to try to get numerical result, you should compare with analytical solutions, and that's why in this preliminary work we have considered a very simple example. Yeah. Okay. Yep. And actually, that's the point, Diego. The interest of these methods is to address high dimensional problems. I mean, we do not try to compete with the methods of Lewinsky, Lyons, Zuazua, Carlos, etc.
Yeah, very interesting. And also is my last question is related to the question of Eduardo. Is you choose the minimal norm control, right? And can you choose different like for instance, when you have the heat equation and you solve control problems with the heat equation, if you compute the minimal norm control, you have some oscillation in the control. And one way to avoid this oscillation is use the Fuzikov-Mandelbilov functional.
Yeah, in the numerical experiments that I have presented in this talk, there are no examples for the heat equation, but in the papers and in the preprints, there are experiments for the heat equation. And actually, the PIN algorithm doesn't generate the control of minimal L2 norm for the heat equation. It generates a smoother control. If you go to the paper, you will see that the control do not oscillate at the final time. It is smoother, right? So, yes, I mean, we can compute controls with which are not of minimal L2 norm. Yes.
And do you know which kind of functional it minimize?
No, not really. I mean, this is like a black box. You minimize a functional, you minimize the PDE, the boundary conditions, the final conditions, and then the algorithm has different contributions to minimize, and we don't know, which one is selected. But the thing is that for the heat equation, we get smooth controls. Yeah.
Okay, very interesting. Okay, thank you very much, Paco, for your very nice talk.
You're welcome. Thank you to all of you. A pleasure.
Is there any other question or comment?